We've got another practice 4 problem coming for you. This time we are doing problem 18.6 if you're following along. This problem, if we take a look at it real quick, is we've got a thin string, so kind of a string, and it's wrapped several times around a pulley, and then it's attached to a block of mass 3 kilograms on one side of it. So over here, kind of drawn it. Here's our pulley. Here's the block. The block's got a mass of 3 kilograms. The pulley is a uniform disc of mass 15 kilograms. So we'll call mass of pulley 15 kilograms. And it has a diameter of 0.7 meters. That means our radius of the pulley is 0.35 meters. That's a very important thing right here. That's a danger word, diameter, because we often want radii when we're talking about this. And we're turning on a frictionless pivot, which is nice because we don't have to worry about any frictional losses of energy. And the block is released from rest, falls through a height h, which we have over here. We don't know what that is. That's what we're looking for. But just before the block hits, we know that when the block ends up down here, it has a speed of 2.65 meters per second. Okay? We're looking for this height h. We know the answer is 1.26. Let's see how we actually set that up. What we're doing in this problem is we're actually conserving energy. If we think back to earlier in the year, we had these boxes or balls or whatever, and we were just dropping them. We were saying that the potential energy we had gravitationally, mgh, well, that just got converted into a kinetic energy, 1/2 mv squared. And that's what's going to be happening here. Our block here is going to fall down and the potential is converted into a kinetic. But this time, we also have to rotate the pulley. The pulley has some mass, it has some moment of inertia, it is rotating. It's going to have a rotational kinetic energy, which is given by 1/2 I omega squared. So it's like 1/2 mv squared, but for angular quantities. So this is an energy problem. We're conserving energy here. Let's think about this. Well, whatever energy we have initially, that has to be the energy we have at the end. So the initial energy has to equal the final energy. And our initial energy here is just due to the block. This 3 kilogram block is just being held there and then it's let go. So initially, we only have this gravitational potential energy. We only have in the beginning the gravitational energy of the block. As that block falls and then it strikes the ground, which we're going to call the ground our reference position, so this has a height of 0 here, we've lost all of the gravitational potential energy. But what we've gained this time is we've gained a kinetic of the block, plus we've gained a kinetic of the pulley. So this is going to be our setup for our equation, what we've got going on here. And let's try to plug some stuff in and see what we can figure out. If we do this, let's just kind of scroll some space real quick. For our block, gravitational potential energy is mgh. So let's just write this all out with variables first, then we'll go back and put in numbers. So we're going to have mgh, and this h is what we want to solve. And this is going to equal 1/2, and I should really subscript this. This is the block right here. 1/2 the mass of the block times the velocity of the block squared, plus 1/2 the, oops, that's not a mass, that's a moment. The moment of inertia of the pulley times the angular velocity of the pulley squared. And I'm looking for h here. So if I want to go and solve this, what we can actually do is we could write this. We know we're going to have to divide by m and g. So we could leave this all up here in the numerator. And if we just throw a big division here, mg, this will actually solve us for h because these have canceled out. And this is the mass of the block. So this is the equation we want to solve for h. Let's just see if we've got all of our numbers here to kind of get this worked out. So if we do this, up here in the mega numerator, we've got a 1/2 the mass of the block, which was 3 kilograms, times the velocity of the block on impact with the floor. And we've got that right up here. That's our 2.65. So times the quantity 2.65, and don't forget to square that. It's very important that you square that for energy. And then this is going to be plus And now we've got, we'll scroll this over a bit. We've got the 1/2 and then the moment of inertia of the pulley. Well, we've got to kind of come back up here to figure out what this is. The pulley is a disc, and we know that the moment of inertia of a disc is going to be 1/2 times the mass times the radius of that disc squared. So in our case here, this is going to be 1/2 times 15 times 0.35 the radius squared. So let's take that big quantity and just tuck it down here. So 1/2 times the moment of inertia of the pulley, which is 1/2 times the mass of, what was that, 15? Times 0.35 squared. So it's 1/2 mr squared, and that right there is the moment of inertia of the pulley. And then our omega, our final velocity, angular velocity squared of the pulley. We don't, let's see, a thin strings are asked several times, block mass. We do not have that quantity. Uh-oh. We'll just leave that there. And then we're going to have to divide this whole thing by the mass of the block, which was 3 kilograms, times g, which is 9.8 meters per second squared. We're running into an issue because all of this here is going to equal h, and we are looking for h. But our other problem here is that while we are looking for h, we do not have this omega squared, which means I have 2 unknown variables and only 1 equation, which means I cannot solve this. So here's what we do. I know that the linear velocity of this block falling, as this block is falling, it has a linear velocity v as it begins to fall. That is pulling on this pulley here, and it's causing the pulley to rotate. And what I know is that a linear velocity is related to an angular velocity by the angular velocity multiplied by the radius of whatever we're kind of rotating here, in this case the pulley. So we can say then that omega is just v over r. And I know what the velocity is linearly when the block hits the ground. That's 2.65. And I know what the radius of the pulley is. So I have now a second equation here so that I can do a substitution method, and with 2 equations and 2 unknowns, I can solve this out. So what we're going to do here is let's get rid of this omega squared, and let's put in the v over r, and we'll make sure we squared that. So our v here is 2.65 over the r of 0.35, and then don't forget to square that quantity. So this quantity here is squared, and then that bookends our entire numerator. Okay, and that will equal h. And these are all just a bunch of numbers now, and those are going to equal some height h. We just need to kind of churn through the numbers here and see what we get. So I like to do this piecemeal. So I'm going to do the 2.65 squared first and do everything here in this kind of green. So 2.65 squared times 3 divided by 2, it gives me 10.5. We'll just round it there. And then that's going to be plus, and then, oh boy, this is going to be a mess. I'm going to do this piecemeal here. I'm going to do 2.65 divided by 0.35. So 2.65 divided by 0.35, dividing by a decimal, number's going to get bigger. So I got 7.57. Then I'm going to square that 7.57. So this in here is 7.57. I'm going to square it. I'm going to get 57. Okay? So now I just like to keep track of things. 1/2 times this whole thing in pink, which I guess we'll get in a second, multiplied by 57.3. And then, so everything up there is the numerator. And then I'll divide by the denominator, 3 times 9.8. That is 29.4. So let's figure out what that moment of inertia is of the pulley. So that's 0.35 squared, because that's in pink, times 15 divided by 2. I get 0.9. I'll just do that as 2, 0.92. And then let's put all of this together now. This is just calculators. 0.92 times 57.3 divided by 2. So here, this gives me 26 point, we'll just call this 3. So now, if I do this, I'm going to have, let's do this in let's do it in red. I've got 10.5 plus 26.3 over 29.4. This is, what is that? 36.8 divided by 29.4. That's going to equal our height. 36.8 divided by 29.4 gives us a value of 1.25, and that's a height, so that is meters. And let's take a look at what our original answer was up here. 1.26, yeah, we got 1.25. We probably rounded somewhere in there because we were kind of crushing off decimals here. So yeah, that looks like a great answer for us in this problem. The key thing here is to recognize that, hey, we are using some conservation of energy. We have the energy of the gravitational potential from the block being up high, the block falling for its kinetic, and the pulley rotating. When we set that up, we had 2 unknown variables, but then we had this lovely second equation up here that we could substitute in and solve everything out. And we just kind of churned through that math. We got our final answer. So with that, this problem's finished. Take it easy. I hope you enjoyed it. It's kind of a neat problem there. So adios.